Hello, today's subject is the Nobel Prize in Physics for the year 1909, awarded to Carl F. Braun and Guglielmo Marconi for the contribution to the development of the wireless telegraphy. And today we're going to look at their Nobel Prizes, lectures, two of them, of course. Of course, there are two laureates. The first is by Carl Braun, Electric Oscillations and Wireless Telegraphy. You see a radio telegraph receiver not invented by Braun, but by a competitor, as you can see. Here we start, of course, summarized by me. In fact, the real Nobel Prize lecture is a little bit longer than this. Wireless telegraphy is the subject, ignoring my, this is of course Braun, experiments on the propagation of electrical wave through water. Marconi had begun his experiments in 1895, reaching a distance of 15 kilometers in 1897. Slebby reached 21 kilometers using balloons with 300 meters of wire. Why was it so difficult to increase the range? Why not simply increase the voltage? It seemed that ever larger antennae were necessary. I, this is of course Braun, started experimenting in 1898 and set myself the task of obtaining a stronger effect from the transmitter. What facts did we follow at the time? The Hertzian oscillations were sensitive to the quality of the spark, lengthening of the spark, and to deleterious effects. Had already pointed to the strong damping of oscillators. Bjerknes in 1891 measured this damping, found the logical decrement for the linear oscillator to be 0.26. Lengthening the spark gap led to a value of 0.410. It was assumed that at low capacities the spark consumed a greater part of the energy. It was also known that the discharge of bigger capacities was also oscillatory. Ferdinand had in 1862 photographed these oscillations. In experimental oscillators, great amounts of energy can be stored, thus can deliver radiated energy for some time. A conduct sparkless antenna could be excited from a Leyden jar circuit of large capacity into potential oscillations that would be more effective transmitter. Three circuits are often this. In figure 1, one sees the direct transmitter earth. Figure 2 shows the inductive circuit, the wiring replaced by a symmetry wire. Shown in the mobile version, we will look at it later. In the Leyden jar circuit, higher voltages are attained in the transmitter than that of a Leyden jar. This is probably a mistake. Yeah, no, that's not a mistake. It was feared that the high losses would make it well, but Wind showed that it would work. I wanted to couple several circuits to increase the power, and the difficulty was to discharge them all at the same time. The solution can be seen in figure 3, an energy coupling. Experiments with these circuits were conducted in 1899. The question was, will the coherer work? That is a device which makes all the circuits fire at the same time, like a resistor and or a capacitor, and can it be replaced? Will buildings and metal masses affect, etc.? All the problems had to be solved almost at the same time. Marconi had also recognized the advantage offered by my circuits from tuned telegraphy. I was able to tune the receiver to the signal. In the receiver, too, the most important circuit was the capacitor circuit coupled to the antenna, passing it to a lossless as possible to the detector. The working of this coupled system is comparable to Overly's pendulum, see figure 4. Energy can travel from oscillating pendulum to the next pendulum if they have the same frequency. The first pendulum is like the Leyden jar, the second like the transmitter. According to the ratio of the capacities, the voltage can be amplified. Oberbeck calculated that if a capacitor circuits operate inductively on a second, in the second a higher and a lower frequency compared to the first occur unless the coupling is very loose. The same is true for the mechanical pendulum as well. See figure 5. This phenomenon is called in acoustics as beating. Well, here you see some of the figures that were just mentioned. Yeah. Okay, we continue. An oscillating tuning fork carries a glass plate covered in soot. The same is done with a second fork of another frequency. Both draw a curve of constant amplitude. See figure 6. The sum of them is seen in figure 7. We will look at that later. Each beating oscillation is thus the superposition of two harmonic oscillators. If this beating oscillation is applied to a structure with the same frequency as one of the two in the signal, it will oscillate in that frequency. It resonates. The receiver has thus to be adjusted to one of the two oscillations. This can be done by a Leiden-jar circuit and has no feedback to the system being investigated. Both oscillations exist in the antenna. In 1902, I investigated the best conditions for receiver. Both parts of the receiver made to oscillate with the same frequency. Search for the receiver. If the oscillation in the receiver circuit by means of coil was transferred into a second coil in the tuned circuit, the intensity of the resonance increased as the two coils moved away from each other. This, of course, within distance limits. The effectiveness have increased with looser couplings in the receiver, but not with looser couplings in the transmitter. Results greater freedom for disturbance in the receiver, a valuable measuring instrument. Frank worked with us, and we were able to construct an apparatus which covered a large range of wavelengths. Donitz made a wave meter named after him, able of attenuating to the measured electrical waves. It was the great help in our investigations and indispensable for the whole field. Wien published on the damping of the coupled transmitter in 1902, and it became a foundation stone. From then out, the measuring were developed, and its result was used in practice by Arco and Randall. The Leiden-jar is still indispensable, using low capacities and high voltage. Installation problems are non-existent, but do exist in the antenna circuit. An accessory which was of great use was the cathode ray tube. Engstrom showed with this tube the hysteresis lagging behind curve. In figure 8, the primary current in the non-capacitive falls away relatively slowly when the circuit is broken. In figure 9, if a capacitor is in, oscillation occurs on breaking the circuit. The current falls more steeply and by nearly twice the value. If this is repeated, see figure 10, with a secondary coil not open but closed, this happened faster and stronger. Figure 11 shows coupled damped capacitor circuit, and one sees beating is the same as the pulsing oscillation. In 1874, they found that materials as galena, pyrite, pyrolusite, tetrahydrite, all metal ores, depart from Ohm's law. They conduct without electrolysis, although they are binary compounds. The resistance depends on the direction and intensity of the current, but they could not explain this unsymmetry. Kohn had similar results, and in 1905 it became possible to use these materials in detectors. Peirce demonstrated the almost complete separation of positive and negative currents in the case of molybdenite. It's unclear whether this will also hold up for rapid oscillations. It was always desirable to me to transmit wave in one direction only. I did this in 1905, but after others did the same. Here you see some of the figures mentioned early in the text. If you want to study them completely, here you see, for instance, an apparatus which can oscillate and make a picture of this. Here you see a picture of it. Here you see a double oscillation, which is added together. You can't, well, etc. If you want to study this more detail, it's probably best to download the PDF from the original site. The link to that will be in the description of the video. In 1902, I found an inclined 10 degrees antenna acts as a directional receiver. A direction transmitter is made with 3 antennae, A, B, and C, see figure 12. The distance CD is equal to a quarter of the wavelengths, and B and C lag a quarter of a cycle behind C. The radiation will prefer the direction CD. So you get an antenna which can transmit in a chosen direction. Next task was to achieve this for rapid oscillations, but first measure those differences. Figure 13 shows the layout used. By adjusting the amplitude in the 3 transmitters in the field, like 14 was created. Today, the study of electrical oscillations supplements that of optical oscillations. The phenomena are analogous. I came to the conclusion that a medium composed of layers of dielectric constant must behave as an unaxial crystal, but the layer's thickness must be a fraction of the wavelength. See figure 15. The layers act like a double breaking crystal if the wavelength is larger than 12 times the thickness of the brick layer. If the number is not 12 but 2.5, the effect of a quarter wave fall of media displays, and Braun gives more details on that, which I have skipped here due to reasons of length. You see the figures displayed to. Here you have the antenna, which can send signals in a specified direction, as you can see here. It shows that we can find an electrical phenomenon starting from an analogous optical phenomenon. Now the reverse. I repeated the Hertzian grid experiments, an electrical phenomenon for visible rays of 10,000 to 100,000 metal wires per millimeter were needed. These were made sending a discharge through a thin metal wire on a glass. The vaporization effect occurs, see figure 16. The metal vapor is driven away, see figure 17, and precipitates in a grid structure on the glass. Parallel polarized light, see figure 18, perpendicular light will show the grid, see figure 19. Braun in 1896 did further work on using other metals. Braun even sees a possibility to use the effect to create better microscopes. Braun himself returned to the Leyden jar circuit, searching for a way to have it switched out automatically after it has given up its energy to the secondary conductor by vaporizing a metal wire. This only succeeded solved with the help of Wien's quench spark and Heidell's mercury spark gap. Those two and Arno came to the final solution in the so-called tone spark. Conclusion: sometimes wireless telegraphy has been described as a spark telegraphy, and so far as a spark in one place or another has been unavailable. Here, however, it has been made as harmless as possible. This is important, for the spark which produces the wave also destroys them, as Saturn destroys his own children. What has pursued here could be truthfully described as sparkless telegraphy. Finishing as I did with these words at the time, I feel happy to think that with the means I have described, we have come appreciably nearer to this target and have hereby made the coupled transmitter more effective. Well, as I said, this is a summary. Not all the argumentation and historiographical details could be taken over. If you want to complete the complete lecture, then you follow this link, and then you have, of course, a more complete picture. Yeah. Here you see some of the illustrations, all the illustrations, which were in the lecture itself. As I said, if you want to study them in detail, you probably best follow this link and download the PDF. Next, the second Nobel Prize lecture for this year, given by Guglielmo Marconi on wireless telegraphic communication. Again, this is not a complete Nobel Prize lecture, it's summarized by me. Here we go. The discoveries of the propagation of electric wave and the application of telegraphy goes hand in hand. Many facts connected with the transmission of electric wave over great distance are not well understood. I almost, which is of course Marconi, never studied physics or electrotechnics, but I was interested. In 1895, I started experiments on transmitting Hertzian waves. Achieving communication with these waves over large distances would outdo all optical methods of communication. I used a Hertz oscillator and a Branly coherer as a detector, and the latter was not good enough. The latter is probably. I then constructed the coherer seen in figure 1, we go to it immediately, which was more reliable. Tuning the coherer to the wavelengths of the transmitter allowed transmission up to about a mile. I used the coherer in a circuit with a voltaic cell and a telegraphy relay actuating another system, which works as a tapper or a trembler and a recording instrument. A telegraphic key in the oscillator was used. An improvement was using reflectors with the transmitters and receivers sending in one direction. The next step, eliminate the influence of obstacles down by earthing, see figure 2 and 3. We'll go to that not immediately, but a little later. I just said immediately, it wasn't right. The higher the used wires or capacity areas, the greater the distance of transmission. Also, larger conductors or capacitors increase the range. The range of the tape message transmissions was increased into steps to 9 miles in 1897. Little electric power was used by the Ruhmkorff coil, and not all understood the breakthrough using elevated capacities and high frequencies and the connection to Earth. Slabby did, see figure 4 for earthing. After numerous tests, the range of transmission was increased to 40 miles in 1899 over the channel, see figure 5. Since 1898, it connected the hearer or detector directly to the aerial and Earth, see figure 6, in which one can also see the oscillation transformer turned to the period of waves received. It did not interfere with other transmitter receivers. A transmitter consisting of a wire discharging through a spark gap is a damped oscillator. It gives its energy off so fast that the oscillations die out fast. In 1899, it improved this, increasing the capacity of the wires by placing adjacently earthed conductors and inserting in series with the aerial inductance coils and increasing the energy storing of the aerial, decreasing its ability to radiate, and now a train of damped oscillator was possible. Here you see some of the figures which were mentioned in the text. As said in the earlier lecture on Braun, if you want to study this in detail, you probably best download the PDF from this address. Okay, see figure 7 and 8. Figure 8 shows a pattern design with an extra oscillation circuit containing a condenser, which improves the resonance of all of the involved circuits. The distance between the oscillating and the radiating circuits was varied, and also the inductance and the capacity had to be correctly adjusted for efficient radiation. Also, the circuit containing the detector and the one with the aerial should resonate. It was possible to use weak electric wave and still send and receive light identical tuning forks. That's resonation. It's also possible to couple one sending conductor several differently tuned transmitters, so different tuned receivers can each pick up one of the different transmission. Another problem, can electric waves be used over very large distances, or does the curve of the Earth be too big an obstacle for this? B by B. Difficulties were also anticipated in the control of the energy necessary for long distance transmissions. All this was solved, but unexpected barriers manifested themselves. Rod Raleigh in 1906 reacted to the transmission over the ocean. The waves must be bended or diffracted. Fleming, figure 11, showed that the waves do not travel the same way as classical Hertzian oscillations, but glide along the surface of the Earth in semiloops. Fleming also gave an explanation, which I have skipped here for length reasons. He also showed that bad conductivity on the surface hinders the wave. The good electric surface of the ocean does not. So it's easier to send messages over long distance over the ocean than over the earth, than over the ground. Thus, communicating in this way is easier over the sea as compared to land. Marconi also observed that banks of sand at sea are a hindrance to the waves. In 1901, Marconi attempted to send electric waves over a distance of 4,000 kilometers, and it would be the possibility of wireless telegraphing between Europe and America. The power used was 25 kilowatts. Assistance was given by Fleming, Vivian, and Entwistle, and the height of the wires had to be increased. You see again some of the apparatus used in the mentioned in the text. Again, if you want to study it in detail, probably best download the PDF. That was too costly. Instead of their numbers and capacity was increased. See figure 13 for the used arrangements. The masts we used were 84 meters high and 60 meters apart. The first receiving station was not ready due to a storm, so a second was improvised. At the end of 1901, the first signals were sent and received. In 1902, the same to the ship SS Philadelphia at the maximum distance of 2100 miles. At this with perfect apparatus. I noticed a detrimental effect of light on the propagation of waves at great distances, halving the maximum distance at day compared to that at night. This is not yet investigated and explained. I think it is due to the absorption during the day is due to electrons coming from the sun in the light of ideas of Arrhenius. Thomson and Fleming have developed similarities, long waves and small amplitudes being less affected than short waves and large amplitudes, as explained by John Thomson. And long waves are more affected, as explained by Fleming. I do not agree with Fleming. In 1902, I observed that even waves as short as 1,000 feet are not obstructed by mountain ranges at night. Here again, some of the figures mentioned in the text. During the day, longer waves of more power was needed to achieve the same. See map figure 16. In 1902, the first official messages were sent along the Atlantic. See figure 17 and 18. Just messages over 3,000 miles only needed the power of 10 kilowatts. And in 1903, press messages could be sent over the ocean. Unfortunate accidents with the apparatus occurred, suspending the service. In 1902, commercial service over this ocean started again and continued uninterrupted for 2 years. An accident suspended service for 4 months, which also gave the opportunity to update the machinery. See figures 19 to 21. The aerial of figure 21 has 200 wires, which were 1,000 feet long, using 8 inner and 16 outer masts. The wavelengths used was 12,000 feet. The final aerial system used is shown in figure 22, and it can radiate receive waves of any length and confine most radiation to a given direction. The limitation of the direction can be improved, but this aerial type is already very useful. Braun, Atom, Melny, and Tosi made suggestions to improve the limiting of direction further. Here you see the equipment. In 1906, I wrote the paper of using horizontal aerials to confine the emitted radiation mainly to the direction of the vertical plane, pointing away for the Earth's end. In a similar manner, it is possible to locate the directions of a sending station. These long-distance stations now used in the recent system for producing continuous or slightly damped oscillations. See figures 23 and 24. Marconi then describes the working of this apparatus, which for length reasons I have skipped. The working results are very efficient resonations of all circuits. Then a high and clear musical note can be transmitted and received or reproduced. Discharges in the atmosphere are heard on the receiving end. See figure 25 for Marconi's magnetic receiver. It decreases magnetic hysteresis, which mainly occurs when dealing with high-frequency signals. In general, the only drawback is that unless very large areas are used, the power that can be employed is limited. The apparatus itself then dissipates very large portion of that energy. Here you see again the apparatus mentioned. The application of the wireless telegraph has resulted in the observation of all kinds of facts that are not easy to explain. Sometimes communication is not possible over relatively short distance, but communication over longer distance is. Sometimes during short periods, the communication over the ocean is impossible. It seems to be the case that waves are reflected or deviated from their path, and mainly in the east-west or west-east, but not in the north-south or south-north directions. Sometimes during sunsets or sunsets shorter waves can travel further than normal. The use of telegraph has become vital for shipping. The same is true for remote islands and the communications in the colonies and newly developed countries. The old countries are also erecting transmission stations to communicate with their colonies. It should be possible to transmit waves around the world, and this without the use of great power, thus relatively cheap. This leaving the ground of fact and entering that of speculation. It was speculation then, it's all achieved now. Well, that was it. As you can see, this was again a summary. If you want to, that means that some argumentations is left out. If you want the read to complete lecture, follow this link, which also will be in the description of the video. That was it for today. Next week we will go to the next year, 1910. For now, thank you for watching, and maybe till another time.